Good morning, ma'am. My name is Rishi Rajput, and today my topic of the presentation is nernst equation applied to electrochemical systems. So, let's start with the introduction. Wilhelm Nernst, a German physicist, received the Nobel Prize in Chemistry in 1920 for the formulation of the third law of thermodynamics. His work helped the establishment of modern physical chemistry since he researched into fields such as thermodynamics and electrochemistry in which the Nernst equation is included. The Nernst equation is a fundamental concept in electrochemistry that describes the relationship between the current density and the potential difference across an electrode. Understanding this equation is crucial for designing and optimizing electrochemical systems such as batteries and fuel cells. In this study, we aim to experimentally investigate the Nernst equation in electrochemical systems and gain insight into the physical structure of the electrode surface using a scanning electron microscopy. In the Nernst equation, the current is proportional to the concentration of the electroactive species, the electrode area, and the diffusion coefficient of the species. The potential difference is related to the standard electrode potential, the temperature, and the concentration of the species in solution. The equation can be modified to include additional factors such as the presence of surface active agents or the effects of mass transport limitations. The Nernst equation can be used to analyze experimental data obtained from electrochemical system by measuring the current passing through an electrode at different potential values. The kinetic of electrode processes can be determined. This information can be used to optimize electrochemical systems for various applications, including energy storage, corrosion prevention, and chemical synthesis. In 1799, Alessandro Volta developed the voltaic cell, that is, the first electrochemical cell comprised of two metal discs, zinc and copper, called electrodes, connected by cardboard soaked with sulfuric acid or saltwater brine as electrolyte. Those were the first studies of storage and electrochemical energy conversion, and several others on battery and fuel cells have been currently developed. In 1836, John Frederick Daniel designed a galvanic cell using two different compartments where happen semi reactions, oxidation and reduction. Anode and cathode are composed of two metallic plates, respectively, zinc in a zinc sulfate solution and copper in a copper sulfate solution. Such two compartments are interconnected by an ionic conductor called salt bridge. The electrodes were cleaned with sandpaper. Afterward, it was immersed in HCl solution to what removes surface oxides. The electrode were cleaned with paper towel and immediately inserted in electrolyte. 50 ml of each electrolyte solution was transferred to beakers. The electrodes were connected to a multimeter and salt bridge was inserted to connect the electrolytes. The electrodes were immersed in electrolyte with 3.2 into 10 to the power minus 3 meters square. The piece out of electrolyte were non-electrochemicals active and has no influence in electrochemical data. The salt bridge and the multimeter was connected and the cell was registered after stable value. The solutions were replaced and the electrodes were cleaned before new potential registration. For cell potential at different temperature, the electrochemical system was inserted into a water thermal bath heated by a heating plate with controller and whose temperature was measured by thermometer. The open circuit potential was measured at different temperature, waiting 10 minutes for galvanic cell to reach thermal equilibrium. So let's proceed with result and discussion. This figure shows cell potential measured experimentally and cell potential calculated by Nernst equation at room temperature for different CO2 plus concentration and fixed Zn2 plus concentration. As new, the cell potential of cell is a contribution of both electrodes. If one electrode has low activity, the cell shown low performance. This figure shows discrepancies between theoretical and experimental Daniell cell with different CO2 plus ions concentration. The Nernst equation can be applied at different CO2 plus ion concentration for theoretical calculation of a cell potential. The experimental result in this figure show the cell potential measured different from theoretical. It is expected the experimental cell potential is lower than theoretical, and this difference can be assigned to experimental random error instead of the accuracy towards minimization. The salt bridge as saturated in KCl was used to minimize the junction potential. Measurement was carried out after cell potential stabilization and triplicate measure were registered. Additionally, the CuSO4 concentration at room temperature showed little change to smaller values. Such changes can be assigned to other physical chemistry properties as ion diffusion from bulk to interface electrode electrolyte, the electrolyte dissociation, and the electrode polarization by mass transfer. According to the Nernst equation, the cell potential behavior is weakly dependent on Cu2 plus concentration electrolyte in all ranges calculated because it is a logarithm mathematical equation, but it do not become the Nernst equation wrong. The values are close to Nernst model. Furthermore, at standard condition, both ions in electrolyte is unitary. Additional investigation of cell potential were decreased out or at different temperature in different copper sulfate concentration and at different temperature and in different copper sulfate and zinc sulfate concentration. This figure shows the variation of cell potential obtained in electrochemical experiment as a function of temperature for the same copper sulfate and zinc sulfate concentration and copper sulfate concentration lower than those of copper sulfate and zinc sulfate. The cell potential decrease with increase in temperature for concentrations different from unity. An important concept shown here and often wrongly used is the use of Nernst equation at temperature different from 25 degrees Celsius. It is not possible to include the Nernst equation calculates because the value of standard potential that appears in this equation is valid only at 25 degrees Celsius. This figure shows the cell potential to Daniell cell at different temperature as a function of only copper concentration. According to this figure, the cell potential shows three well-marked regions of concentration relative for all temperatures. The first from 1 to zero point 0.8 mole per liter shows no variation in cell potential regardless of temperature. The second from zero point 0.8 to zero point 0.4 mole per liter shows an approximately 4% decrease in cell potential with copper sulfate concentration decrease, all independent from cell temperature. Finally, the third region comprised of copper concentration lower than zero point 0.4 mole per liter where the cell potential drastically mainly for high temperatures.